Hello everyone, my name is Dominic Baloi from Orbit TVET College. I'm going to be giving lessons on Applied Engineering Technology Level 4. On our last session, we were doing a beam. We were calculating the reactions. We also drew the shear force diagram, and then we also calculated the bending moments at each force on the beam, as you can see on the board. So today, we're going to proceed with the same beam so that we can indicate to you how is our bending moment graph going to look like. And from that bending moment graph, we will then be able to see what is the maximum bending moment and the minimum bending moment. And then from there, we will make an additional question to our beam so that you understand how to calculate the maximum bending moment of the beam when you are given the stress that is acting within the beam. Remember that we gave you a definition of stress, stress being a force that a beam experiences internally when other forces are acting externally on the beam. So on the very same beam, we've got forces that are acting externally, as you can see. We've got the top forces that are pressurizing the beam upwards from the upward direction. Then we've got forces, or what we call the reactions rather, that are reacting to the forces that are acting on the beam. So from now, we're going to plot the values that we have calculated for the bending moments of this beam on the very same set of axes where we drew our shear force diagram. So our first point is bending moments at A, meaning that this is our starting point. We've got bending moments at A. But when we go to bending moments at B, what value are we getting? We are getting a positive value that is taking us to 138.75. So we're now going to draw our bending moment graph. It's going in a slope direction because between the forces we don't have a UDL. You will see as it changes when we are dealing with a UDL that is on top of our beam. The shape changes. We are no longer going to slope, but we're going to go down in a parabolic form. So now we have a value of 138.75. From that point, we're now going to bending moments at C. Bending moments at C, it's taking us to minus 225. So meaning that we're going to go from C to minus 225, of which it will be that point. We're now going to slope to our point. Remember that the drawings that we are now having are not being drawn to scale. So a question will come to you whether we're going to give you a scale, maybe to say to you that for every meter you must use 1 centimeter on your ruler to draw the graphs, meaning that your graphs are going to be more accurate than mine, and then the shape that you have of your shear force diagram and the shape that we're going to have of our bending moment graph will be the same. So we have now drawn the point at C, of which is minus 225 Newton meters. So we're now going to go to bending moments at D. Our bending moments at D is the last point of our beam, meaning that it's 0. But we are also able to prove it that bending moments at D is 0. Sometimes it is not advisable that you just say bending moments at D is 0. But you must write it in full to prove to the marker or the examiner that you are able to express understanding when it comes to the calculations of this beam. So from this point, from C now going to D, we no longer have a UDL, meaning that we're going to go back to the sloping part that we were doing from the first portion before we started with the UDL. So we're now going to slope back to 0. We now slope back to 0. So that is the shape of our bending moment graph. So from this bending moment graph, we can now say this is our maximum bending moment and this is our minimum bending moment on the graph. So sometimes it happens that they say we have a formula of calculating the maximum bending moment of the graph, and it is given by maximum bending moment is equals to stress times the sectional modulus of the beam. After we have drawn the bending moment graph, there's a possibility that you might have a question that says calculate the stress that is experienced within the beam. Normally what they would do is that they will give you the value of the sectional modulus of which it is represented by S. You would find that the beam can either be a square, a rectangular beam, a round beam. Sometimes it can be a round tube. Sometimes it can be a rectangular tube. Sometimes it can be a square tube. So having that information, they will give you that the sectional modulus of this beam, assuming that it is a square beam, they will give you the value to say that the sectional modulus is equals to 0.5 cubic meters. Then they say to you, from this information that you have, where you have drawn the bending moment graph of that beam, calculate the internal stress that the beam experiences. The formula that we have to calculate stress is that formula where we would normally calculate the maximum bending moment to be equals to stress times the sectional modulus. So in this case, we're going to need the maximum bending moment. Where are we going to find the maximum bending moment? Our maximum bending moment, it is represented on our graph. Our graph represents, the top part of our graph represents maximum bending moment, and the bottom part represents the minimum bending moment. Meaning that we can replace this value onto our formula together with the sectional modulus that we were given for the beam. Meaning that we're going to have 138.75 being equals to what we want to calculate, stress, times 0.5 of our sectional modulus. So for us to calculate stress, we're now going to say 138.75 divided by 0.5, of which we can now get our stress. Our stress is measured in pascals, meaning that we are talking to pressure. The formula for pressure, it's force that is applied over a certain area. So now we're going to have 138.75 divide 0.5. Then we get that our stress is 277.5 pascals. Sometimes they would represent Pascal as being kilopascal, of which it has a prefix of kilo. Sometimes it can be megapascals, of which you would then refer to the prefixes that we use in engineering to indicate much bigger values. So in this case, this will be our stress for our particular beam. But they would continue to differ given the types of beams that you will be given. From here, I would like us to recap what we have been doing. We started by calculating the reactions F and G. Our reason for calculating our reactions is to make sure that we determine the strength of our beam, whether our beam can sustain the types of forces that is being exerted on our beam. So how we do that is that firstly you need to check your beam. Is my beam having a UDL or not? The first example that we started with, we did not have a UDL, meaning that you can go directly into calculating the reactions. So on this particular beam, the first step that you do, you start by making sure that you make your UDL a point load. We gave the definition of a point load when we started with our presentation to say that a point load, an example of a point load will be this 190. It means that it is acting on a particular point on our beam. Then our UDL, the meaning of our UDL, it means that it is a uniformly distributed load, meaning that our UDL acts for a distance of 6 meters. But for every meter, you've got a force of 20 newtons being applied. That's what gave birth to that amount of 120, meaning that you're going to have 20 newtons for every meter. But our beam or our UDL acts for a distance of 6 meters. Meaning that for us to make a point load of a force, we're going to eliminate meter, cancels meter. Then 6 times 20, we're having 120 newtons acting downwards on the center of the distance 6. That is why we have 120 on the center of 6, meaning that we've got 3 meters on the other half of the beam, 3 meters on the other half of the beam. That is the first step that you do to make sure that you convert your UDL into a point load. Then the next step is that you're now going to make F the fulcrum point. You're going to start by taking moments at F. Remember that moments is a force that acts at a particular distance around the fulcrum. So when you make F, we take moments at F, we make F our fulcrum point. Then from there you check which forces from this fulcrum point are going in the clockwise direction and which forces in the fulcrum are going in the anti-clock direction. The most important information that you must not miss is that the reactions F and G are also forces. Remember that we spoke about Newton's law 3 that says that for every action, there's an equal reaction in the opposite direction. Meaning that when you are applying force downwards, there's an equal force being applied in the opposite direction. That is Newton's law number 3. So after you have made F your fulcrum point, or you have took moments at F, it means that G is also a force, but where is it going? You need to make the right determination to say that G is going in the anti-clockwise direction. So you'll be having all these forces that are going clockwise except for G that is going in the opposite direction. For us to say that moments at F, the total sum of clockwise moments is equals to the total sum of anti-clockwise moments. It's because of Newton's law 3 to say that for any force that is going clockwise, in the direction of the clockwise, it's equals to the force that is going in the direction of the anti-clockwise. So that's what gives birth to this formula. So after making or writing this formula down, you then look at the forces, all of them that are going in the clockwise direction. You write them on one side, and then you'll be having G that is going in anti-clockwise. It will only be G, the force that will be going in the anti-clockwise direction. Then you write G on the anti-clockwise. Then you are able to calculate the value of G. From there, you need not be confused. You must remember that for you to take moments at F, it means that you want to be able to calculate the balance that you're going to get from G, reaction G. From there, after calculating G, you then say, okay, now I'm going to take my moments around G, meaning that you make G your fulcrum point, meaning that your beam now is going to rotate around G. Whatever force that will be exerted on the beam, they are just going to rotate around G. G will become our pivot point or our fulcrum point. So from here, you also make a determination to say, on this point, if G is my fulcrum point, where are these forces pushing the beam? In which directions are they pushing the beam? You start by 90 to say, okay, this force is pushing my beam in the clockwise direction. But 70 and 90, they are pushing my beam in the anti-clockwise direction. Meaning that from the formula that you're going to have in saying that moments at G, the sum of clockwise moments is equals to the sum of anti-clockwise moments. You will now have values for clockwise, you will now have values for anti-clock. But you must always remember that you will be calculating the value of reaction F. Where will reaction F be driving your beam? In what direction? You can see that F will be taking your beam in the clockwise direction. But you must remember a very critical information to say, if you've got a force that is on the same axis with your reaction, you must ignore the value of that force when it is on the same axis with your fulcrum point at that particular time. Because when we were taking moments at F, we did not make consideration of 90, but we made consideration of 80, even when it was on the same axis with G. The reason for that was because 80 was not on the fulcrum point at that particular time. So that's why a lot of students you will find them making mistakes on the beam. It's because they are confusing that information. So now I believe that is a little bit clearer to you. That is how you make a determination. From there onwards, after getting the values of F and G, your reactions, you will now go to draw your shear force diagram. Remember that your shear force diagram, for every force that is going down, you say that it's a negative. For every force that is going up, you say that is a positive. So you will be having 90 going down, F going up as a positive, and then they will give you a value, either positive or negative, depending on the amounts. But the difference comes when you are dealing with a UDL. Remember on our previous examples that when we were drawing our shear force diagram, we did not at any point slope on our graphs. We were just moving horizontally and vertically only. But now, because we have a UDL, it is critical information to remember to say, when we are dealing with a uniformly distributed load, it means that we're going to slope because it is no longer a point load that will either go up or down. So we're going to slope. That is information that you need to remember. From there, we went on to calculate the bending moments of the very same graph. If you remember, the first examples that we made of calculating a bending moment, we did not have a UDL. We just calculated the bending moments without considering any UDL because it was not there. But on this particular graph, you must remember critical information to say, after calculating bending moments at B, when you are doing bending moments at C, you must make consideration of the uniformly distributed load. How do you make consideration of that UDL? It means that the UDL, the value that you have of the force that is being applied per meter, you need to convert it so that it becomes a point load. So in this case, we converted the 20 Newton per meter to become 120. Then we said, okay, because we are doing bending moments at C, the 120 comes before C, but what is the distance to C? It does not become 6, it becomes 3, because from 120 to C, the distance is 3. Another important information that you must remember is that the very same UDL is now going to apply when you are calculating bending moments at D. But because your UDL acts for only 6 meters, it means you're going to make a point load taking into consideration the total distance of your UDL, of which is 6. It gave us 120 newtons. But when we are calculating bending moments at D, you're going to take the very same value of 120 to the distance, times the distance to D, meaning that it's going to be 3 plus the remainder of the distance, of which is 2,5. I have seen a lot of students confusing that in my experience, confusing the distances to say that, but why, when we calculate bending moments at D, we're no longer using 3. We are using an additional value. The reason for that is because from this particular force to the bending moments at D, we multiply it by the distance from this force to D, of which is going to be 3 plus the additional 2,5, and it's going to give us 5.5. From there, you're going to draw your bending moment graph. The bending moment graph, it always slopes. If you have seen in our previous example, we slope everywhere, meaning that we're going to go in that shape, that shape, that shape, if we don't have a UDL. But because in this particular beam we're having a UDL, it means that where there is a UDL, we're going to draw the shape of a parabola. That is the shape that we have used here. A parabolic shape instead of us sloping. That is critical information that you must remember. To say that, oh, I have a UDL on the beam, it means that when I'm drawing my bending moment graph, rather, it means that I need to have a parabolic shape everywhere where I have a UDL. So that is how you draw your bending moment graph. After drawing the bending moment graph, a question might arise. Remember that examiners, they differ. Others would end their questions here. But others will then proceed to say, but what about the stress that we have explained, to say it is a force that a beam experiences internally. Remember that all beams are made of atoms, and everything on this planet, it is made out of atoms. And those atoms, they've got a particular strength that they have, and it can be maintained up to a certain limit. So when we calculate stress, we check what kind or what level of stress exists when the beam is under this type of a pressure. Pressure from forces coming from the top going down, and also the pressure that is coming from the reactional forces that are balancing the topward forces. It means that you are talking to the atoms that exist in the beam. Remember that once a beam, it is under pressure, depending on the type of beam that we have. Maybe the beam consists of an FCC structure, body-centered cubic, meaning that it's got an atom, a big atom in the center, and small atoms at the corners. It means that when we apply too much pressure, you can create a fracture on how the atomic structure is. And once you create a fracture on the atomic structure, it means that your beam is ultimately going to fail. The result of a beam failure is when you have buildings collapsing. That's when you have bridges collapsing. And unfortunately, that is a kind of disaster that we don't want as human beings, because the collapse of bridges means that either lives will be taken or lives will be at danger because that bridge is not safe. But this is critical for us to make sure that we protect ourselves from such disasters by making sure that the types of beams that we use on our buildings, on the aeroplanes, on the trains, on the cars, they are of the necessary strength for that particular job that they have to do. Because you must remember that in engineering, there is one critical thing that we teach you, is that use the correct tools for the job. Meaning that this beam is going to act as a tool for us to be able to build a huge building or a building with many floors. So you must make sure that you pick the correct one so that it's got the necessary strength to support all the loads that is going to experience, and to make sure that the internal strength that the beam has, it's going to sustain the pressures that it will be experiencing outside. I hope that you enjoyed this session, and then you will be able to pass this part of your examination, and this critical information, it stays with you forever so that it grows you to become a very well-equipped engineer in the near future, so that you can assist our country in becoming a better country. Thank you very much. Other sessions will follow as time goes by, and then we will cover other topics on the book that we have or the syllabus that we have, so that we assist you in making sure that you have a better understanding of the subject, and then you can do well on the subject. I thank you.